Okay, so this is chapter 14, High Amplification Comparators, what we're going to learn in this chapter. Okay, so we learned something about diode indicators, and they're inexpensive, widely used and reliable, but within their capability and their shortcomings. So when we use them as comparator, they're very reliable, especially when we're measuring so close to the zero setting as possible. And the chief method of amplification is nothing but boosting the precision, okay? Is their gear train. So better means of amplification for comparison measurement are developed with other mechanical options, optical, pneumatic, and electronic. So anyways, these are the modes for amplifications. But do nothing but to amplify the precision and so that you can measure in a more accurate way. So gauges and measurement instruments. Gauges are used primarily to check or inspect. We always use them to check or inspect something or parts. And gauges and measuring equipment standards are as shown in my next picture on the next slide. So error gauges are high amplification instruments, and they are properly called pneumatic comparators, and they compare parts with masters, okay, and they can inspect tiny hole diameters, so very good, okay, standard. So we have gauge. It's nothing but, if we go by GAGE, that's a mechanical artifact of high precision used either for checking a part off or checking the accuracy of a machine. If we go by GAUG, gauge, okay, a measuring device with a proportional range and some form of indicator, either analog or digital. So this is gauges and measuring equipment, and you can see right here you have lean standards, master gauge, and you have inspection gauges, you have manufacturer's gauges, non-precision measuring equipment, precision measuring equipment, comparators, optical comparators, and gauges. So we have many different kinds of gauges and measuring equipment. So most of them are for used as standards, okay, for inspection, for checking. And when you go into precision, that's going to 1,000 of an inch or finer. So precision is nothing but finer measurement that we're doing. When you go into comparators, again, precision measuring equipment, okay, for comparative measurements between the work and a contact standard, okay, again, use. So standards, we have gauge and gauge blocks, and they're used for precision measuring equipment. Then we can go into optics, and that's your next chapter. It's a very important chapter, and you have to really study to understand optics. So that's chapter 16. So optical comparators and gauges are again those which apply optical methods of magnification exclusively. Okay, now again to analog and digital instruments is pretty easy. So most of us, modern consumer electronics have propelled us from a completely analog world into the digital world. So we use a lot of digital readouts now because they're pretty easy to read. So analog instruments use almost any physical quantity to correspond to numbers. A digital instrument deals again with numbers, okay, directly. So it is easy. High amplification comparators. We go 1 million to 1 amplification, and that's been created by using again optics, optical, mechanical, and electronic devices for the centuries. Okay, now high amplification mechanical comparators. So diode indicators with high amplification, okay, can be refined, but they can also misplace a decimal point. Okay, even if we go into high amplification, sometimes we're going to get a misplacement, okay, of the decimal point. So a digital indicator mechanism is a cascade of stages, so each on a higher amplification. So error in the gearing at the final stage has a relatively small effect on accuracy, whereas an error in a stage close to the input has a tremendous effect on the accuracy. Okay, so at high amplification, that means that when you go up to very high amplification in your measuring devices, okay, what can happen is you can lose a decimal in accuracy, and that often happens. Okay, so here you have 1 inch, and then you go down each decimal. Your first one is your 0.1, your second decimal is your 10 mil, and then the third one is 1 mil, and then the fourth one is a 1/10 mil, okay, and so on. So as you go up in high amplification, you're gonna lose a decimal, and that happens quite a lot. So high amplification mechanical comparators. So right here, just a little gear, and it's just showing you gear set in this picture has been replaced with a precision steel ball, okay, rolling along a finely lapped sapphire surface. Extreme minute changes in position of the spindle, okay, are directly translated to this gear train. So when you look at the picture, you can see what we're trying to do to the dial indicator is we substitute a more accurate linear, okay, to rotary transducer than the rack and pinion in your dial indicator. So what we get is a higher amplification, okay, measuring device. So the instrument now, by changing that, is now capable of 0.00002, okay, inches discrimination. So you can go all the way down to 1, 2, 3, 4, 5 decimal places. So that's a pretty high amplification. Okay, so here in this picture, we're getting rid of friction. Okay, so all friction is eliminated except for the intermolecular frictions, very minute friction inside. And the twisted band, okay, is fixed at one end and connected to the spindle at the other end, and attached to the pointer in the center. Just trying to tell you how we design a high amplification comparators so that we can enhance the precision of this instrument. So this completely mechanical instrument, we have eliminated all friction with this design, except intermolecular friction is still there. Okay, so the amplification we get by this design is 100 and 100 times, so that's 100,000 times. Okay. Alright, the next one is your read type comparator. So read type comparator is like the previous instrument because it requires only intermolecular friction to achieve its amplification and to support all its moving parts. So it uses optical lever method to achieve additional amplification. So here you can see the metrological features and the functional features. So I don't know why in this textbook they always give these features in a picture. So if you take a look at your metro features, you can see it's about the same as other high amplification mechanical instruments. They're relatively inflexible in configurations in how rigid they are and standing on its own anvil. Compared with the great flexibility of the new electronic instruments. Okay, electronic instruments are they're more flexible than these mechanical ones. So however, there's never any doubt about their geometry. So this adherence to, again, your Apes law is completely clear, although it may not be with their electronic counterparts. Okay. So the read mechanism uses the optical lever to amplify the reaction. So a prism, okay, is going to use instead of this mirror. So an optical lever is used to amplify the reaction. So in the actual instrument, the optical path is longer, okay, than is shown here. And then again, we're going to use a prism instead of a mirror. So when you take a look at the figure, you're going to see the mechanical parts right there for the read type comparator. You don't really have to know everything if you can be able to understand. Okay, this is here, we have your main read, and then we have a fixed block right there, and then we have a movable block right there, and then our spindle is down there. And that's for your fine adjustment, okay, on sleep. And here is your guide reads. So here we have our lamp, your lamps is right in there, and then your target, this little one is right there. So if you take a look at it, that's just your scale that you can be able to see. Then you can also have a mirror or a prism on the other side. So that's how we amplify and indicate the scale, so that we can go on to higher amplification. So here just a diagram is showing, how the angles, okay, right here, these angles are going to amplify the scale. And then here, this is your fixed block, and then this is your spindle right there. And again, if you just scan the picture and try to understand, oh, this looks like a read and it's using the optic, and if you can be able to get that, that's all right for this course. Read type instruments are available in a range of amplifications with either metric or English scale. So we have metric and we have English, and here again metric, and then here is your English scale. We call it British actually scale. So that's your 1000 to 1. Here's a 10,000 to 1 amplification. Electronic measurements. Electronic measurements are very popular because the advantages of these instruments are primarily functional, okay? And your electronic instruments reduce again your time lag. So it saves a lot of time for you to do the measurement, not like the mechanical ones. So I remember like some students struggling how to read the micrometer second scale. Okay, everybody can read the main scale, but when it comes to the second scale, you have to do interpolation a little bit, yeah. So that takes some time. But for when you have your digital vernier caliper, it's pretty easy. All you have to just zero set and measure, and you can be able to read your decimal, okay, values very easily. So anyway, so electronic measurement, we have our metrological and then functional features. And you can read all of this. These points are just your generalities, and any one of them might be sufficient reason to accept or reject an electronic instrument, okay, for a particular measurement. Alright, power amplification for measurement. So we have our inertia and the friction. So make sure you review your physics if you do not know the difference, alright? So for a friction is you have a resistance, okay, against your force, and also we have a gravity pulling it down. Your inertia again, just a tendency of an object to stay at rest, tendency of the object to preserve its state in motion. So that's your inertia. So it can severely limit mechanical instruments. So both of them, okay, they can limit your mechanical instruments, but electrical system, they don't have these issues. So their power amplification, the ability to convert a mechanical motion into an electrical signal, can be electronically amplified. Alright, so all the energy required to operate the instrument had to be generated by the action of the part on the instrument called loading. So they use power from the outside source to generate rockets. of the measurements, but also to use the readout signal to control machines or processes. So without electronic instruments automation or numerical control of machines, that would be very impossible. Okay. Generalized measurement system. So here all measurement instruments, okay, are described by the generalized system. So that's nothing but your length, your mass, and then your time. So including those that measure your mass, also your time, as well as your length measurement fall into, again, the generalized system. So here are the typical systems here. Instruments, your test indicator, dial indicator, read type. We have electronic, and then another one is your pneumatic. So input signal is going to be your length, okay? For pneumatic, it's going to be your change in separation. So this is your detector transducer. So we're going to do the contacting lever arm. Now this one is a contacting spindle and rack. And this is contacting spindle and reed block. And this is contacting variable circuit element and your exit, okay, orifice. So here your intermediate modifying state is your lever arm, gear train and pointer arm, parallel reed mechanism and optical lever, electronic amplifier, and flow meter. Loading. We have input signal, all of them, okay, all the way down. For electronic comparator, you have input signal and auxiliary source. Pneumatic comparator, you have input signal and auxiliary source. So for readout, it's going to be hand on the scale, okay? For indicator, hand on the scale. For read type, you have shadow on scale. Electronic comparator, you have electric meter. Pneumatic comparator, you have flow meter too. Electronic instruments use simplified bridge circuit. So this is just showing you what electronic instruments usually use. So the simplified bridge circuits is similar to those used in electronic comparators, and it's about the same. And some use special transformers, and they're called a linear variable differential transformer, and we call it a VDT, okay? Some people call it lifted, but then I just call it LVDT. So this is an LVDT, okay? So it gives an output voltage that is proportionally linear to linear changes in core position. So when you take a look at it, you have your secondary, okay, this is your first primary coil. You have coil 1 is your secondary, and coil 2 is your also secondary. And then you have your core inside, and the motion to be indicated is on here. And you have your insulating foam. Then we have a constant AC voltage, and we have a difference voltage output. It's right there, okay? So anyway, you don't have to go into detail. All you have to know is about your electronic instruments. They use a bridge circuit, and they use the transformers, okay? Alright, so gauge head. So here in this picture, so there are 3 gauge heads, of which the frictionless type is the least common but the most sensitive. So the gauge head is not totally without friction, so there is still intermolecular friction in the reeds. So an LVDT is also called a gauge head, okay? There are 3 main designs again for gauge heads using LVDT transducer inside. So these items are only the detector elements of the gauging system. So you have your probe head, you have your cartridge head, and you have your frictionless head. And they are the 3 most popular, okay, gauge heads. They're electronic and using the LVDT transducers. So here, this is your figure 1414, and it's showing some typical characteristics in the 3 major gauge heads. So all use your LVDTs, okay, that's your transducer elements. So here we can see your comparison gauge heads. It's just trying to show that 3, your probe, your cartridge, and then your frictionless type, okay, your 3 gauge heads. So repeatability, this is not reliability, this is repeatability. Okay, so here you can see the decimal places, so 1, 2, 3, 4, 5, 6. This one is 1, 2, 3, 4, 5, 6, 7. And that one is 1, 2, 3, 4, 5, 6, 7. Okay, that's 4. And then that's 8 for the 7 amplification. And this is your 6 amplification is 1. Your gauging pressure is going to go this way. Your spindle trouble, you don't have to know all of that. That's just happening inside of the head. And then the spindle trouble, the 0 position, is about the same. So this just showing you the relative sensitivity of these gauges head. Okay. So sensitivity is with this line, you can be able to understand. So we call it the repeatability. We know that the cartridge, this type, is somewhat more sensitive, okay, because it has 7 and then it has the highest. Then the probe type, but the frictional type is twice as sensitive as the probe type. Okay, so here the same thing. So these particular values apply to the gauge heads shown way back in chapter 10, figure 13. Okay, so those of the other manufacturers may be different. But now all you have to know is we have 3 gauge heads. Alright, you have your probe cartridge. Cartridge is more sensitive, and then frictionless type is more sensitive. Alright, probe type, gauge head, the very first one. So the probe type gauge head is called a probe head or indicator head. So it's attached to an arm, okay, and extensively used for high gauge measurements. So the probe head consists essentially of a housing, a transducer, probe tip, and lever assemblies. So when you take a look at it here, you're going to see a lever arm right there, and this is your contact force spring. A little spring right there, and that's your LVDT, and this is your pivot, and this is your probe. So probe heads differ considerably, but all have similar features. So the adjustable probe acts on a LVDT cartridge and a housing for convenient mounting. Okay. So standardized probe head mountings are covered by an EGD specification, and probe head can be used in a variety of positions. So many positions here are possible with a probe head. So when you take a look at the first one, you're going to see adjust head to best angle to clear work. Second one here, this is your probe. So keep the tip angle with work less than 15 degrees. These are all your measurements. So next work is right here. The tip has 12-degree range of positions. Okay. So although reversible heads are available, the majority of probe heads measure in only one direction. So this is your height gauge stand on. Here is your probe. Okay, this is your angle. That's your 0 scale, +3 and then -3. So the direction of movement is only one, okay, direction. So that movement must be remembered. So to operate in the opposite direction, you're going to simply turn the head 180 degrees. Cosine error. So everything that comes with your angle is going to be having this type of cosine error. Okay, affects probe head measurements as the angle, again, increases. The amount of vertical movement required to encompass the same arc, that's your arc, increases. So here is your equal arc, and that's your A, and that's your B angle. So it takes considerably greater trouble of the contact in B to produce the same arc that was produced by the trouble, okay, of the contact in A. So going that little distance, and this is your little distance. So when you take a look at it, right, so you get the same arc. See here, equal arcs. The same way like you're traveling, okay? The cosine error is dependent on the probe position. So when you take a look at it, this line, you're going to see your probe type, okay? This is your gauge head. The contact angle is 0, so cosine angle is 0 because there's no angle. And that's just your work or gauge block. So now our contact angle is at 5 degrees. So now we're going to start to see cosine error is plus 0.38%. Okay, that just depends on your scale. Contact angle 10 degree cosine error is going to be plus 1.5%. Contact angle here 10 degree cosine error plus 1.5. Contact angle going up 15 cosine error plus 3.4%. So when you take a look at it, so contact angle 0 going all the way to 15, and you see cosine error going 0% to 3.4%, going up, very proportional. 20 cosine error is at 6% now, 30 angle, okay? So here's your probe, your angle is measuring from 0 like that. So 30, your cosine error is 13.4%, going up together. So therefore, cosine error is dependent on the probe position, making the angle between your measuring object right there, and that's your reference line. So 1420, the plus error in the instrument results in a plus error in the reading, but a minus error in the actual part size. Minus error is always okay with your part, and it depends on your part size. And your plus error again results in a plus error again in your reading, minus error in your part. So don't forget that. So here the effect of the instrument error is reversed on the part. Instrument error also decreases actual size, and minus instrument error increases actual size. Effect of instrument error. So when you take a look at it here, so we have 1.000, so instrument zeroed on 1.00 standard, okay? So now 1.004 standard is going to give 1.005 reading. So the instrument has 20% plus error. Now we're going to measure part. That's just calibration because you're using a standard here. This is just a 0 setting, okay? And your standard is at 1. Your standard 1.004. Now we're going to measure our part. So instrument is going to read 1.004. So correcting for error, the true value is 1.0003. So what do we have? 1.003 because the instrument is reading 1.004. Here we already understand if we measure the standard 1.0004, the reading is 1.005. Therefore, you're going to take 1 unit out in order for us to be able to get the correct reading. Okay. So the reverse is also true. When you zero the comparator close to the actual part size, you minimize the cosine error in the reading, which you can reduce even further by using the 10-to-1 rule. So here is showing when cosine error cannot be avoided, it may be minimized by using a standard close to the part size and by using the rule of 10-to-1 to select the proper scale. So here when you take a look at it, your standard is 1.000, your part is 1.026. your scale is 0.001 scale. This is the same scale, and that's 0.00001 scales, a bit higher. So we're going to write that down. Scale, and then your standard, okay, and then your reading on the standard is going to be 0. The reading on the part is 0.030. The parent size is 1.030. The cosine error is 0.004. So the actual size that we've got is 1.026. Again, don't worry about how to read precisely, okay? At scale, the same one, the standard is here, 1.1030. Reading on the standard got to be 0. Reading on the part is 0.005. Apparent size, you add them up. Your cosine error is 0.0005. And your actual size is 1.026. Again, your cosine error depends on your probe position, okay, and the angle right here. So in this case, you're measuring with the 0.134 for that error. Again, you don't have to worry about it, just scan through this. And then your best scale, we're going down 1 decimal. So your scale is 0.0001. Your standard is 1.026, okay? Standard has changed. We do the same things. Reading on the standard is just at 0. Reading on the part is 0. So apparent size, you add them up. The cosine error, since the reading, okay, is completely 0, you have nothing. So that's a 0 right there. And your actual size is going to be, you add them up. Yeah. Since there's no cosine error, so this measurement device is the best. Gauging force can be mistaken as gauging pressure. So people always think the pressure is the force, but they're different. Okay, pressure is nothing but you're looking at the force on a particular area. So make sure you review your physics. Okay, F, okay, divided by A, your area is equal to P. So gauging force must be applied as low as possible, so don't put so much force. So most probe head instruments are designed so that this applied gauging force can be adjusted. So the gauging force is proportional to the displacement in the instrument, so therefore instrument can be set for minimum or maximum displacement. So your probe head is very sensitive, so when you do the measurement with the probe head, you have to be very careful, okay, and don't put a lot of force on it because you're going to make mistake. So the probe head may be set either for maximum travel or minimum gauging force. So here just showing you, how it's going. So the center line is your 0 on the scale. So if you go that way, and you're making this arc, which is your angle, and that's your plus 0.030. Okay, your pressure is 95 grams contact force. And then you have 5 grams contact force in that area. Okay, so minus 0.003. So when you apply the force on a particular area, you're going to get your pressure. The screw for adjusting contact force is right there. The tip travel at maximum contact force at 100 grams using 0.001 scale. So now we have 8 grams, you have plus 0.003. On that side, on this side is minus 0.003. And you've got 11 grams force and you have 5 grams contact force. So say the force is lower, that one is really high. So the tip is going to travel at minimum contact force. And the scale we're using is 0.0001 for this trouble. So here, from here to here, is a big arc, and that's your total tip trouble, the tip of your probe. Okay, and that's 0.006. When you want to trouble from here to here, you have like a 0.060. Okay, and you have a bigger force right there. And the trouble is maximum contact force, about 100 grams. Okay, using 0.001 scale. Okay, so we have frictionless gauge head. It's the most sensitive gauge head. And again, we're using the LVDT transducer. Okay, for this device, and this instrument is used mostly for calibration. So the frictionless gauge head is not convenient as probe and cartridge heads. All the moving parts, okay, are in one continuous axis, and that is supported by two parallel flexure reeds. So here you can see a frictionless gauge head. And you don't have to go into details. All you have to know is frictionless gauge head. We use the LVDT transducer, okay? And we have two flexure reeds. And if you can remember that, that'll be great. Then here, a frictionless gauge heads. Okay, the one that we can see on the other side, the bigger one. And they use a flexure, okay, springs. So here you can see right there, contact force spring right there, okay, spring suspensions right there to support the moving parts. So they're used when the highest precision is required. The cylindrical type bottom has the same Zeiss mounting system as dial indicators, making it interchangeable again method, okay, measurement and indicator setups. So however, these may not have all the other features needed to fully utilize the capability of the frictionless heads. So here that's your contact and that's your spindle. Cylindrical gauge head is almost as versatile as the probe head. So here you can see in this picture, so they have the same diameter as a dial indicator, therefore you can use cylindrical head, okay, in place of dial indicator. So here you can see your high gauge stand arm, and here is your locking knob, and this is your replaceable probe tip. Again, that's your tip. Okay, for this particular device, that's a 3 by 8 inch mounting diameter. So you're just looking at the probe type head and a cylindrical head, which is this one. That's your probe, and that's your cylindrical head. Okay. See the difference is kind of pointed, and this one is completely. This is taking the shape of a cylinder, so therefore we call it cylindrical gauge head. Electrical amplifier and meter. So the principal advantage of electronic measurement system is again minimization or even absence of mechanical parts. Okay, and the errors these parts can cause. Those mechanical parts, they have inertia, friction, so therefore they always have errors. So by using the electronic measurement, we're getting rid of these errors. So the manufacturers have reduced friction, again, inertia to a minimum, okay, in the meters that display the readings, just like in the gauge heads using the transducers. Precision instruments are carefully used in precision labs. In practical industrial use, okay, these instruments suffer abuse because in industry, the operators don't care. They do like whatever, okay. Therefore, when we use the data coming out from the floor, we have to do a lot of adjustment. Okay, we call it raw data. Raw data are raw because the instruments are being abused. Okay, they never follow any kind of rules that there is in the world. I don't want you to be the operators. I want you to be the managers, okay, and investigators who is going to make sure everything is right, not somebody who's going to mess everything up, right? So electronic display helps eliminate friction. So the same principles on mechanical instruments are applied to fully electronic instruments. Just trying to tell you, electronic instruments, they have fewer errors because we're getting rid of errors caused by mechanical parts. It stands for electronic comparators. So when we use electronic comparators, we don't want to hold it all the time, so we want to put it on a stand. So the higher the amplification of your instrument, the more critical the positional relationships become. Positional, so therefore we use a stand. So the theoretically ideal instrument gives us reliability to gain range and versatility, okay? So now we're getting into the stand to get reliable measurement. So high amplification comparator, they require stands, okay? That is going to combine rigidity with ease of operation. So here you can see the gear rock, and then your column, and this is your base of your stand. And that's your head and locking knob to lock it. And that's your coat adjustment. Okay, and then you have your height knob as well on it. Then you have your settled, and this is your gauge part. This is where we're going to put all the parts that is in the world. And here is your 3 anvil points, and that's your anvil. And this is your spindle tip. And that's your clamping bracket. And that's your cover, we don't need it. And then we have our gauge head right in there. And that's your cylindrical gauge head. And then we have our fine adjustment. Stands for electronic comparator, same thing. So the construction of stands must combine 3 qualities. Okay, one is the stand must provide positional relationships sufficiently accurate for the measurement to be performed. Otherwise, we don't want to use this stand. It must be sufficiently rigid that the ideal instrument is approximated during measurement. They got to be rigid. It must be readily adjustable so that its part size may be changed quickly and without danger of damage. Okay, and they got to be readily adjustable. So 3 points: positional relationship, rigidity, and adjustability. Reference surfaces. The high amplification comparators usually use separate anvil, okay, that are attached to the stands as a reference surface. Now, effect of temperature. So reliable measurements depend on the clean measurement conditions, correct positional relationship, the use of measurement instrument with much higher precision than the tolerance of the measuring part. And the measurement system, again, must be kept cool. Okay, must be kept cool. So most engineering materials expand, okay, when their temperature rises, okay, at different rates. So here your physics review and your also chemistry also. So if you have less heat, okay, here inside it's just a display of your molecule. So the kinds all stay together, okay, they're not moving too much. So the more heat you get from a source of energy, and it's going to energize these little guys inside, okay? So now the molecules are energized, meaning that they use the heat. So heat is nothing but energy transfer of energy. So the energy has been transferred from a heat source into them. So therefore they can use that energy and then start to move. Yeah, we have only 2 different energy. One is a potential energy. Potential meaning you're staying in one position or a space or place in a space, okay? And you have a potential to move, okay? So as soon as you get a transfer of heat, meaning like transfer of energy, okay, you start to move. So as soon as you start to move, you start to take place in a space, okay? And we got expansion, yeah? Okay, so for the rigid instruments, okay, rigid parts also behave the same as your little molecules right in there because all of them are made of elements. Elements are down to atoms, and atoms have all kinds of little things inside, which are your electrons, neutrons, and protons, okay? And these little things can be able to take out energy so easily and fast. So every time they pick something up from the environment, okay, environment temperature, they start to expand. You can't see it with your naked eye, but they're happening inside of their own structure. So it takes much longer for a part to cool, okay, than it does for a part to warm up. Same thing here, you put right here is your part, okay, it's heating. So this is your time to heat. So we can see your thermal expansion. Cooling, we're cooling the part down. Time to cool. When you look at the time to heat and time to cool down takes more time than time to heat it, okay? And this is your length back to your normal. And here you can see your thermal expansion of your part. Yeah? So we're just trying to measure how much is your thermal expansion with high amplification, yeah? Measuring system. And again, you can see with our regular eyes at all. So if you think about the macro example, or like the sun, okay, sun is a exploding. You can call it exploding fireball, okay. Yeah, our Earth is a cooling down planet. So our Earth was a star, okay, it was a star. It was exploding, burning, just like our sun right now. But then it cooled down. It takes millions and millions and millions and millions and millions of years to cool down. And one of the miracles is us appearing on this earth. Yeah? So same as that, all the parts, same thing. It's really fast to heat up, but it takes longer time to cool it down. So we gotta take steps to reduce the errors generated by inconsistency in temperature. But first, we must identify the ways heat is transmitted by convection, radiation, and conduction. So these are just the heat transmission. So what you have to do is you're going to review your physics, okay? I'm not going to get into it and teach you physics. Okay, so when a problem arises, examine all the factors that can result in errors, especially in including heat considerations. So that's a figure 1428. So all sources of potential error should be consciously investigated whenever a high precision measurement is made. So here is your measurement system right there, your part is right there that you want to study, okay? So we have a heat from electric light, okay? We have avoid direct drafts right there, okay? And here we have heat from direct sunlight, and we have to pay attention for all of that. Sources of comparative measurement error, okay? So your gauge blocks must be in good condition, recently calibrated, and ran properly. So handle parts and gauge block as little as possible, don't touch too much. So locking knobs must be tight, otherwise it's not going to be holding it in the right way. Handling stand by column can cause errors from uneven heat expansion. The outside vibration again can affect the measurement. You're going to use a 3-point anvil. The gauge head must be securely clamped. So use insulated forceps to handle gauge blocks. So differences between part and gauge blocks in material compressibility, temperature, and surface finish, they can cause error, okay? So here if I ask you, okay, go ahead and study this and give me all the sources of error, you have to come up with all of that, okay? Okay, applications unique to electronic measurement. The differential measurement comparator, they provide measurement information from algebraic sum of signal, okay, from two pickup heads. The differential comparators measure concentricity, roundness, parallelism, and similar part features with relatively high precision and without expensive special fixtures. So the amplifier for differential measurement has places for 2 input channels and 2 additional switches to select the mode of operation. So this is what it looks like for the differential measurement instrument. Another one is difference measurement. Okay, they're not the same. Differential is differential and difference is difference. So in generalized difference measurement, the 2 gauge heads are aligned along parallel lines of measurements on the same side of the part. So you can see your standard and then your part. So this is just a general setup for difference measurement. Okay, then you have your head A and head B. And this is your D, it's your difference between that 2 parallel lines. So alternative measurement method minimizes temperature expansion and contraction. So we're always looking for how to eliminate the temperature error. So this is one way that we can be able to do it, the elimination of variable, that's your temperature, by using difference measurement. So the thermal expansion provides an example of elimination of a variable by means of difference measurement. So don't take everything for granted. Okay, people who are in science and who are in engineering, technology, we have to do a lot of work. Okay, each person gonna do a lot of work, precision work, in order for us to be able to build the building that is gonna stay on the on the ground against the gravity to certain period of time, and also to stabilize right there at that position, standing against all kinds of weather that can happen, come from a lot of measurements. Okay, so don't take it for granted. Don't insult people who study, who develop these methods, because they have to really sit down and come up with a lot of work, okay, for all the things that you have outside for granted to happen. Okay, that comes from centuries and centuries of knowledge, and it's not a joke. Okay, the more you study, the more you will respect ancient people. Okay, ancient people are also today's people, including you and me. We have to do a great deal of study and work hard, okay, for us to be able to continue this civilization into the future. So here, when you look at it, you're going to see the zero set at 68 degrees. Okay, so we have our single channel measurement right there, and then you have your part, the temperature is 68. Now the same part, the temperature is going up at 80, so part has plus error already. Okay, to do expansion, every time we come to the plus error, that's your reading error. Minus error is in the instrument. Difference measurement we're going to start to use, and we're going to zero set at 68. Okay, your part at 68, our temperature is going up at 80. Okay, so here we have same part, and we have no expansion error because we're using difference measurement. Okay, here we've got error because we're not using difference measurement, we use just a single channel measurement. So difference measurement is when we do using 2 heads at the same time. Yeah, so we have standard, we have standard and part, we have standard and part at different temperatures. So other errors can also be eliminated. So you can see in 1431. So this is another setup. So only the difference in concentricity this time is shown, okay, on the indicator. So if both parts are out of round in the same amount, the reading is not affected. So just trying to use the 2 heads, okay, for the concentricity. Okay, so another one here in difference measurement is your 2 gauge heads are placed parallel, okay, on a taper part. So it's possible to check the degree of taper without regard to its diameter. So the taper must be set to a master, meaning like that's just a standard. So here we have 2 heads, so therefore we know we're doing a difference measurement. So by placing 2 gauge heads parallel on a taper part, it's possible to check the degree of taper without regard to its diameter. Okay, so the taper must be set again to master. Okay, that's just it. Some measurement is another measurement. So two gauge heads are aligned, okay, along the same line of measurement, but again, this time is opposite sides of the part. So here's your part, first head, and then your second head. They are on opposite sides. So the part can also move perpendicular to the line of measurement, because this is your part, and the line of measurement is right there. So therefore, the part is moving perpendicular to the line of measurement without changing the measurement. So if you want me to draw it, okay, this is your movement, and then you can see the perpendicularity right there. So this is just an example of some measurement using the opposite bands. Okay, so the general precautions for reliable comparison measurement with differential measurements, the very first one. So reliability checklist for reliable comparison measurement, so from 1 all the way to 11, and you can read it in the handout. So we're thinking about the temperature considerations, okay? It's been added to this checklist because of their importance in high amplification measurement. Okay, metrological advantages of multiple scales. So an instrument with several scales, okay, one instrument but you have different scale, like micrometer, you have main scale, and then you have a smaller scale, okay, on the side. Vernier caliper, the same thing, you have a digital readout scale, which is going to the decimal, 3 decimals, and you have the main scale. So an instrument with several scales is versatile and can take the place of several separate instruments for comparator applications. So here, this pictures or table is showing you the typical scale selection, how we're going to select the scale. So here they have selected two of them, 0.02 and 0.001 inch. So comparator application, this is your height gauge applications. So for comparative application, your production, thus your applying parts, agricultural machinery parts, builders hardware parts, plastic parts, small casting, and small forgings. So to engage inspection, okay, we do not recommend to use this scale. And you can read the entire table in the handout, okay, under figure 1435. It's just trying to show you how to select the scale. So metrological advantages of multiple scales. So it's difficult to zero set a high amplification comparator with only one scale. So therefore we need to use multiple scale and high amplification comparators. So zero setting single scale instruments right here. So the problem with zero setting a high amplification comparator that has only one scale are often even more difficult, okay, than this example. So here at rest, so lower onto part that has handmade, okay, full turn 3 or 1 or 2, okay. So here it seems it's really difficult to, what it's trying to say is it's difficult to control, okay, because it's a high amplification comparator. So using one scale is really difficult. You have to lower again, and then you insert the part right there. It looks good, but okay, but zero setting and too close to the end of the range again. So here replace the standard and start all over again. So you have to do that again and again in order for you to be able to get the correct zero setting if you use only one scale. Okay, now you're going to use a multiple scale instrument. So the lower scale can be used to find the higher scales as needed. So here is zero setting multiple scale instruments. That's the comparative stand is in the back. It's not shown in the picture. You always need one for high amplification instrument. So the multiple scale selection usually provide the best amplification for each row in which the instrument is used. So first we're going to set 0.001 scale, okay? So lower head onto the stand until close to 0. So 0 set with coarse adjustment and then switch to 0.0005 scale. Okay, we're using the close adjustment and the fine adjustment 2 knots. So use the stand adjustment until hand is close to 0, and then 0 set with the coarse adjustment. Okay, so we can be able to set 0.001 scale. So continue until on size scale and make final 0 sets with a fine adjustment. So now we get a perfect 0 setting right there. We use a stand adjustment, and then we use a coarse adjustment. The dispersion of reading does not cause a problem if it is entirely within tolerance. So what's trying to say is that dispersion of the reading doesn't cause a problem as long as it is entirely within the tolerance. Okay, it's got to be within the tolerance. So here we have our tolerance zone. If you keep it in the tolerance, you're not going to get the dispersion of reading. It's not going to give you any kind of issue. So here my plus and minus, and this is our zone of uncertainty, and that's our discrimination. Okay, 0.002 is a desired tolerance right there. And this is our zone of uncertainty. So this zone is within the tolerance zone. So therefore the dispersion of reading is not going to cause any kind of issue. Here is a minus and plus. Okay, that's your tolerance zone. And we can see the reading right in here, but it's okay. Okay. So here are the examples showing that the apparent reading may be very different from the actual size because of the instrument uncertainty. So you have your actual size and you're measuring it, and you're going to get your reading, which is your apparent reading. Okay, and that's because of the instrument uncertainty is there with the instrument. So therefore your reading, apparent reading, is not going to justify your actual size. So just trying to tell you, apparent reading is going to be different, okay, from the actual size because of the instrument uncertainty. So here, actual size is right there, your tolerance is right here, but you're reading like that. So actual size is right here, your tolerance is right there, you're reading like this. Actual size is here, your tolerance is right there, you're reading like this. And the actual size is right over here, and then your tolerance is right there, and then your reading is, okay, right here. And that can happen. Okay, so zone of uncertainty is compensated, right? We want to compensate the zone uncertainty zone to reduce that apparent reading, so to error. So to achieve reliable measurement, we want to compensate that zone of uncertainty that is giving us issue. So in order for you to get a reliability, you have to get rid of all the issues, okay? The same thing, some students cannot be able to do the assignments, so you're not reliable in your duty, okay, as a scholar. So why are you not reliable? You can't do your job of studying and doing your assignments because you have issues, okay? You have some sort of issues, and you have to eliminate that in order for you to be able to do your assignment, same as that. So the objectives maybe not to reject any good parts or not to accept any bad parts. An allowance must be made for the zones of uncertainty. So this is now linking to the manufacturing, okay? So what we're trying to say is we make the parts, and then that got to be within the tolerance zone, okay? And sometimes our measurement is going to be completely compensated with the uncertainty, so the reading is messed up. So in order for us to be able to get the accurate reading, you have to compensate your uncertainty zone, okay? So here, the allowance must be made for the zones of uncertainty. Here, discrimination divides the tolerance in two parts. So here we can see the range, okay, that passes all good parts. So that's a 50% additional range at each limit thereby passes bad parts. So here the zone is right there, but then we have more, okay, additional range. So we are passing not only good parts, we're also passing the bad parts. So here the range, okay, is going to reject all bad parts. We're reducing, see, that range, okay, and now we have a 0.000. So 50% of the tolerance range, okay, thereby removed from each limit. So from here we get rid of that. So therefore, we're going to allow only the good part. Discrimination divides tolerance in 4 parts. So the higher discrimination reduces the lost range, okay, for good parts, and then the additional range, okay, for bad parts. We don't want the additional range because we don't want to let the bad parts, okay, pass. So we want to get rid of it. So we use higher discrimination, so that is going to reduce the additional range for your bad parts to pass. That is going to also reduce the loss range for good parts. So the good parts can passing is going to be accurate. Good parts passing is going to be accurate. So here range, okay, that passes all good parts, 25% additional range at each limit, okay, and they're going to pass the bad parts. We don't want that. So here range, okay, is going to reject all bad parts because 25% of tolerance range is going to be removed, okay, from each limit. So therefore we will reject all bad parts. So that's a good setting here. So when the instrument has sufficient discrimination to divide the tolerance into 10 parts, only 10% of range gives trouble at each limit. Only 10% is going to give you issue. So here, when the instrument has sufficient discrimination to divide the tolerance into 10 parts, we divide into 10 parts, okay, only 10% of that range is going to give you issue. So here, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and we're getting rid of 2 parts out of 10. Here also 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's the entire 10. So range that pass all good parts, 10%. Right here, additional range. Okay, at each limit, thereby passes bad parts. We're giving each 10% on each side. Okay, so we have 12 instead of 10. So that will let the bad parts all pass. So here range is going to reject. Okay, we're getting 10% cut right there. We have only 1, 2, 3, 4, 5, 6, 7, 8, 9 right here. Okay, so here is 5 and here's 5, so altogether 10. So 10% of tolerance range thereby removed from each limit. So therefore that's going to reject all bad parts. If you look at the number, so from here to here is 0.0002. So from here to here is 0.0002, 4. So on each side we have 0.00002 on each side. Okay. The same thing from here to here is 0.00016. From here to here is 0.0002. Okay. So you're gonna subtract this from that and then divide it by 2 will give you each zone. Okay. Alright, in a control operation, most of the parts are grouped in 1/3 of the tolerance and few parts fall into the areas of the limits of the tolerance. So here I was telling you, when you look at it in a typical manufacturing operation, most of the parts will be ignored, okay, close to an average size. So the purpose of quality control, that is S, is to ensure that the average is close to the basic desired size, okay. Average is so important in QC. Okay, we want to make it close to the basic desired size. Desired size is what's your boss determine, okay, what's the stakeholders and the CEO want it. So they're playing with the money. So if they want to make more money or profit, then they are going to specify this desired size. So everybody got to produce within that specification limit. Okay. So that's a QC is going to check that specification and the average. So here we have your tolerance again. That's a 99, 3 by 4%. That's a 95, 1 by 2% half. Okay, and that's a 68%. Okay, we already know these are standard deviations. If you give the tolerance that big, and everything is going to pass, good or bad. So some people will be getting some defects of some sort in your new product box. And that happens quite a lot from Walmart, right? Walmart products. Okay, there's a 95 here and 99, so that's almost close to 6 sigma, yeah? So 6 sigma right there. This is about, this is going to be like about 3. Okay, so best scale for the measurements of the most sensitive scale that contains a tolerance of the dimension to be measured should always be selected. So for unskilled worker, okay, they're not very good. So they must start with lower scale. You don't want to give high amplification to the unskilled worker. They're going to abuse it. And you want to gradually train them to use a high amplification scale, okay, so that they can be able to handle it. Digital instruments, okay, with electronic system, the signal conditioning and display unit are independent again of your sensor standards and setup. So the greater the precision of the instrument with respect to the tolerance, the smaller the zones of the uncertainty. Okay, the greater the precision, the smaller the uncertainty zone. Okay, it makes sense. So with a multiple scale instrument, 10-to-1 rule is used. An electronic gauge provides readings in the uncertainty zone of the dial indicator. So here we have a tolerance, a zone of uncertainty. Okay, so 1/5 division is scarcely visible, you can't really see it. So the same amount of uncertainty. Okay, here's that's the mechanical, and this is our digital. So the amount of uncertainty is distinctly visible, okay, on the 0.00005 scale on the electronic comparator. So both of these instruments fulfill the requirements of 10-to-1 rule. So electronic gauge provides readings in the uncertainty zone of the dial indicator. We're going to minimize the observational errors with high amplification comparators. So these comparators can be used in some calibration procedures, and we use it to minimize errors, okay, caused by field and eliminate computational errors. So what they do is they minimize the field variable, okay, in some calibrations and eliminate the computational errors. So here when you look at it, there's your gauge. So in this setup, the error is arrived at by algebraic addition of gauge block length and vernier reading right there. Okay, that's your vernier. You determine that's a vernier because you have a jaw right there, see, movable jaw, and that's just a standard fixed jaw. Gauging force, okay, may create errors. So you have a gauging force, and then we'll look at that, it's kind of like leaning a little bit, yeah, because of too much force. So error is read directly on electronic comparator after setting vernier to gauge block length, okay. We can use a high amplification comparator, connect it to the vernier, and then measure the part, okay. So in that way, we can get rid of the computational errors. So, okay, calibration of high amplification comparator. So in calibration of high amplification comparators, the gauge blocks must be accurate enough, okay? These gauge blocks, you have to make sure they're accurate enough for the instrument, and then they must be free of damages, okay, again, for precision measurement because we're using them as standards. Now, calibration of high amplification comparators, we're gonna hit the positional relationships, and they got to be known, they got to be within adequate tolerances, and they got to be secure. Okay, so the accuracy of high amplification comparators are stated in percentage again, okay, of full scale deflection or the range. So the percentage must be evaluated in terms of magnitude of error. So the error percentage versus magnitude, and you can see that too. So the percentage of error remains the same, but the magnitude varies with total distance travel. In calibration, it is desirable to stretch out travel to find the errors, okay? So whereas in the use of instruments, the reverse is true. So here the scale is being checked, 0.0005, okay, inches per division. So your instrument error, they said, is 1%. So the top is just showing you the use of the instrument. The reverse is true because here when you look at it, it's going to here 0.015, okay, and here is 0.00020, okay, and you have two different scales right there, your standard scale and then your coarse adjustment. And here reference at the end of the scale, okay. Here the reference is at the center. The reference is nothing but where your zero setting is. So here you can see the zero setting is on the side, and here the zero setting is in the center, yeah? And then it's going the same discrimination to the side. Here is going that way, yeah? So therefore you have instrument error. This way is a little bit better. The calibration of how amplification comparators. This picture is showing you how the calibration points vary for multiple scale instruments. So in multiple scale instrument, the percentage of error is going to be the same for all scales, right? But the magnitude is going to vary, okay, and it's proportional to the amplification. And you have to know that if measurement is restricted, okay, to 1/3 of the total scale range, and that's a shaded, okay, portion right there in the instrument. So the capability of these instruments exceed, okay, general measuring capability in all scale except the lowest amplification. So here you can see the scale, okay, 0.001 inch per division, and B is 0.0003, and your C is going to be 0.0001. Okay. So A scale, and then so B is going to give you a maximum error, and then C is going to give you a working error. So what is showing here on the number, it's just trying to tell you the magnitude, okay, of that error is going to be proportional to your amplification. So the more the amplification is going up, okay, so when you look at here, that's 0.005, okay, here is 0.001, and here is 0.005, okay, and here is 0.00001. The more zeros, the higher the amplification, because it can read the finer, okay, more decimal points mean you can read finer discrimination, okay, therefore it's a higher amplification. So the higher the amplification it goes, okay, the magnitude of error is going to go up. So you can see the magnitude of error right here, okay. And that's just showing you the division. That's your standard division right there, giving you the amplification, yeah. So the more amplifications, the magnitude of error going up. So if lowest scale is used, the error would appear as uncertainty in one portion of the scale only. So when you look at here, okay, on A, which is 1440A, that's a low scale and independent errors. So if you use a lower scale, the error would appear as uncertainty in one portion of the scale only. Then we go to B, okay, on higher scale, the gauge head error is going to encompass the entire scale range. Then we go to the higher scale, okay, so the result of the gauge head error at the high amplification scale, where a dependent error condition, and we can see that, okay. But just these little symbols, don't feel bad about it. Some people don't like symbols. They're just telling you, okay, that's a dependent error and that's a correlated error dependent, so therefore there's no connection in the symbol. Correlated, they are correlated, okay. And here is the totally independent errors, okay. So this example is just trying to show you, okay, and assume the error in one portion of the gauge head range. It's just with an assumed error, a linear amplifier, and a meter with an error in one portion of its range. So the relationship of these error changes, okay, with amplification of the system. Do not confuse with the English word, okay. For English word dependent, meaning you're depending, so you might think like the symbol got to be connected or something, but it doesn't work like that. Okay, for dependent errors, we usually show the symbol like that. Independent in English is you're independent, so therefore there shouldn't be any kind of connection. But independent errors symbol, we go this way. Okay, I don't know why, it's the opposite of the language. So don't get into it. Anyway, I'm not going to ask you there, so you don't have to worry about too much. Just concentrate on the simple MCQs and very short answers with blanks, okay? Because metrology has incredible amount of knowledge, and all we want you to know is just read, okay, at least 1 or 2 times, and know what kind of instruments we have, because we have no idea of, okay, which company you're going to end up, and they all are going to be using some sort of metrological instrument, okay? So you will definitely come to a position where you have to use them. And if you have foundation, okay, knowledge, then you should be good. Okay, that's it for chapter 14.